I'm Ivan, and this is DPL Labs. Today's video is about investment casting technology, also known as lost wax or burnout casting. Specifically, we'll be talking about casting into a ceramic shell and mold based on a water-based silicate binder. What are the advantages of this technology compared to others, such as casting in a chill mold in molding sand or other methods? First of all, this technology imposes virtually no limitations on the geometry of the model. The only exception is channels with a diameter of up to 4 millimeters. Those are more challenging, but there are still ways to solve these issues. But overall, this technology doesn't have the same restrictions as, for example, casting in a chill mold or molding sand. The second advantage of this technology is the high surface quality of the model. Since the suspension used to apply the ceramic shell has a very fine-grained structure, with the filler being of the F1200 fraction, the resulting surface roughness can be extremely minimal. The third advantage is high-temperature casting. In other words, this technology is frequently used in industry to cast complex turbine blades and turbojet engine parts from a special alloy called Inconel. In fact, this is considered to be the main advantage of this technology, making a model from a material that can be melted or burned out in the process. In our case, we will use PLA plastic, which is simply a 3D printed model. It has a relatively low amount of ash residue left after burnout, making it especially well suited for this particular purpose. For example, I have prepared a piston model to demonstrate this. This specific model cannot be produced using other casting technologies, mainly because it contains internal cavities. You cannot achieve this result with milling, die casting, or any other available technologies. Right now it's actually in the slicer. We print it using PLA plastic and then demonstrate the next steps in the process. So we've printed our model out of PLA plastic and attached the sprue here because this part needs to be printed in this orientation and this one in that orientation. And now we're applying our ceramic shell from a slurry with a binder, sprinkling everything with filler for about 5 to 8 layers, and we'll end up with a ceramic shell mold. The next stage of the process, following the creation of the wax or burnout model, is to carefully prepare a slurry mixture from a binder and a filler. The filler is made up of extremely fine-grained refractory materials, typically around F1200. As a filler, you can use electrocorundum, which is aluminum oxide, or marshallite, which is silicon oxide, or other refractory materials. On average, approximately 2 kilograms of filler material are needed per kilogram of binder solution to prepare the slurry. The essence of the technology is that the model is dipped into the binder and then sprinkled with a coarser filler around F40. However, for the first layers, the fraction can vary from F80, and for the final layers, an even coarser fraction is used. The coarse filler, which is a material with a relatively large particle size, serves solely to significantly speed up the buildup of the layer during the process. The binder suspension itself, once it has been fully cured and solidified, forms the final ceramic structure. In this particular case, electrocorundum was specifically utilized. F1200 with filler results, essentially in aluminosilicate ceramics. With a coarse fraction filler, you also obtain this type of ceramic shell. To form a shell suitable for casting, it is necessary to apply approximately 4 to 8 layers, with intermediate drying periods between each layer, continuing until the shell is completely dry and the binder has fully set. Afterwards, the mold is carefully calcined, which means that first, the original model is either melted out or burned out. Then, the mold itself is calcined. And finally, the molten metal is poured into the prepared mold. As you can see, this mold is cracked. This is the part where the sprue was. Here, we specifically utilized electrocorundum as both the filler and the coating. Perhaps we didn't follow some part of the technological process. But this ceramic turns out to be very unstable when exposed to temperature fluctuations. That is, even if it is, say, heated up to 600 degrees, but while it is being taken out of the muffle furnace, it cools down a little, and then aluminum is poured in, the temperature difference causes it to crack immediately. We want to try making ceramics completely from silicon, meaning that as a filler material, we will use marshallite as the coating, and also quartz sand F40. Perhaps by using these proportions, the ceramic will be more stable against temperature fluctuations.
So we're starting to carefully prepare the mixture for dipping our mold.
So now we're going to carefully apply the ceramic shell itself by dipping our mold into the ceramic slurry mixture. First, I'll carefully pour the slurry inside, making sure to do it gently. First, I simply dip the object into the solution, making sure it is fully coated on all sides. The process here involves applying a layer of electrocorundum, which is the material used for coating in this particular case. After this step, the coated object is left to dry for about an hour, allowing the layer to harden and adhere properly. This process is repeated several times, usually applying between 5 and 8 layers in total to gradually build up the shell. Each layer is important for achieving the necessary thickness and strength. While waiting for the layers to dry, I decided to lighten the mood a bit. In a bold move, I tried to distract everyone from their work by suggesting we take a break and organize a barbecue, hoping to bring some fun and relaxation to the group. Vanya, seriously, you really need to drop everything right now. How long can you work? Let's fry some meat. So we burned our plastic in a muffle, the mold was fired, and now we have a ready-made ceramic shell into which we can pour metal. Now we carefully cover it with sand, then put the muffle back in to heat up to the proper casting temperature. After that, we take it out and pour in the molten aluminum. This is more or less how it looks. The shell completely replicates the shape of the plastic part. So we are filling the mold with sand. First we pour it inside, actually. We open it like this, gently lifting the cover with a small plate. After opening, all the necessary items are carefully placed inside here, making sure that everything is arranged neatly and is easy to reach when needed. And then we simply cover the whole mold with sand. The main thing is, what I really want to emphasize here,
Lift your hands so there's something to grab onto later.
we've placed the sand-covered mold into the muffle furnace to heat it up to casting temperature, about 620 degrees. Now, we just wait for it to heat up, and then we'll pour in the aluminum.
Here's our main melting furnace.
It's made from a gas cylinder, a jet, and a tip component from a semi-automatic welder, specifically.
It all runs on propane, which is actually very convenient. It's quite environmentally friendly compared to any other type of fuel. Now,
We take out the crucible with the molten aluminum and wait for the aluminum to cool down to casting temperature. It shouldn't be red. Now we remove the slag. We have remnants from previous attempts at making a ceramic mold. There's also various other slag. Right now you can see that the aluminum is overheated. The temperature for casting is excessive. There are many dissolved gases now. If you pour it like this, there will be many pores. It needs to cool down, and then we'll go ahead and pour it. Oh, nice, it's so warm. We're gently and slightly heating the sprue from above, so that crystallization doesn't start at the top, but happens gradually. After a while, we'll see what we've got. Alright, let's gently take our mold out of the sand, the one we've poured. Now, we'll let it sit for a bit longer and allow it to cool down. And then we'll see what we've got. Now we're cooling down our mold. So, our casting has now cooled down completely, and the ceramic shell is gradually coming off. Here we can already see a casting defect, a crust on the sprue. It's unclear whether it's present in the part itself. We're about to find out. Maybe the sprue itself is just wrong here. Tada, we can see a cavity here, which is a type of casting defect. This cavity is quite deep, mainly due to shrinkage that happened during the cooling process. The sprue, which is the channel through which the molten material was poured, was made incorrectly. The shape of the sprue needs to be changed. As for the casting quality itself, it is actually quite remarkable. You can even see the individual layers that result from the 3D printing process. You can also clearly see the faceting created by the 3D printer itself. Here, you can even see the seam from the 3D printer where the joint was made. So this method perfectly reproduces the geometry, the ribbed layers, the seam, and also the inner surface, capturing all of these details with impressive accuracy. Here the ceramic is gradually coming off. Here we can see the bosses. Now we'll knock all of this off. So in conclusion, we can say that the technology works overall. The level of detail is excellent. You can see every layer. The only thing we haven't mastered yet is that we're not foundry specialists, so we don't know how to position the sprues correctly. Because of that, we ended up with this defect, a shrinkage cavity inside the part itself. So overall, the technology is really quite good. It works very well, and we will definitely continue developing and exploring this topic further. Please subscribe to the channel, give us a like, and goodbye everyone.